So yeah, it is customary for those who don't know to, before the defense, do a presentation in TU Delft that explains in a high level what the research was about of the thesis. So that's what I'm about to do now. So yeah, the dissertation is called Generalizable Robotic Imitation Learning, and as a subtitle, it has the topics interactive learning and inductive bias. I hope this is going to be a bit more clear at the end of the presentation what this actually means. So let's start by the motivation. We are picturing ourselves in a world with robots. So maybe we have robots in our houses helping us with our daily tasks, or maybe also we have them in topics that might be a bit more urgent, such as the fat reduction process. So maybe robots that are harvesting tomatoes in greenhouses. So it sounds like it would be great to have robots in these situations, but then if this is the case, where are the robots? Why don't we have them yet? So the thing is that it is actually challenging to have robots in the wild. And by in the wild, I mean outside typical industrial settings. So normally when you have robots in the industry, they follow fixed solutions. So they are very repetitive and always do the same. And the conditions are very controlled. So maybe the objects always have the same shape, maybe we know exactly when they're going to arrive, and nothing unexpected is going to happen. So then, yeah, in this case, it is actually possible to have nice solutions, but otherwise it becomes more challenging. In the real world, if we want to have robots in the wild, for example, in houses, every kitchen might be different. Also, every preference of different people might be different. So it becomes very challenging to have specific solutions for every possible situation. Also, robot must react in real time to things that could happen. So, for example, we have people walking around the robots. The robot must avoid the people, don't collide with them, and react safely. And these things makes the problem a bit more difficult. So let's see a bit how the process of building robotic systems work and why this is actually giving us problems. So commonly, first, we have a robotic system. So this is basically a robot. Then we have someone that knows how to program a robot and give it in some way a brain, such that then we reach a solution. So far, so good. The thing is that actually in practice, we have people interacting, in this case, with the robot expert. So maybe in the industry, we have a person that is telling, I don't know, every couple of months to this expert to reprogram the robot, or imagine that we have multiple houses around the world, and each person needs some expert actually programming the robot. The problem with this is that it doesn't scale. It becomes intractable. So how can we solve this? One way of addressing this is actually removing this middleman from this process. What if, instead of having this person, we directly get robotic behaviors from the users of these applications, and we don't need a middleman? Maybe this would help us. So to address this, my research has focused on the problem of imitation learning. In this case, every person that doesn't necessarily need to know about robotics is able to teach robot behaviors, for example, by demonstration. So in this video, I was grabbing the robot around and moving it to, in this case, pick a tomato. And this, we could use this as a robot demonstration, along with many others, trying to consider different situations that the robot may be around, such that we actually tell the robot what it should do. To do this, I only need to know how the problem should be solved, but I don't really need to know too much about robotics. Ideally, after doing this, the robot would be able to learn the behavior we wanted to learn. So here, the robot started from two different parts of the space, but then it was actually able to move and pick this tomato. So the thing about imitation learning is that it offers the opportunity for non-experts to easily encode complex behaviors in robots. And this is very promising. So great. If this is so great, where are the robots again? Why we don't see them around? So to understand this a bit better, let's take a closer look at imitation learning. Sorry, 1 second. Yeah. So in imitation learning, we have the robot. In this case, we have a star, where we want the robot to get after some point. And also here in the side, we have this small brain that is some type of computer or algorithm that is actually telling the robot what to do. So in this case, let's imagine that we haven't showed anything, the robot, about what it should do, so it doesn't know what to do. It should reach the star while doing some specific shape. In this case, we have this red trajectory that is actually going nowhere, so it's not really working. So what we could do is control the robot, in this case, for example, with a joystick, or by moving it around, as what I showed before, and tell it what it should do, which is actually this blue trajectory. We could give this blue trajectory to the brain of the robot and make it learn from it. Now, the brain should be a bit smarter, and actually, when we put the robot in the same initial condition, it should do the trajectory that we want it to do. So far, so good. Let's think now that we could also put the robot in different positions in the space, and we don't have data here. We haven't showed the robot what it should do, so it shouldn't know. Again, we have these red trajectories that go nowhere. So we just can collect more data, give it into the robot algorithm or brain. We train it, we make it smarter. And now, from these initial conditions, the robot also knows what to do. So this makes sense, but here I'm ignoring a part of the problem which is actually very important, which is the concept of generalization. What happens if we have data from different parts of the space and we put the robot in a region where we didn't have a demonstration? Ideally, if the robot is smart enough when it's learning, since it is in a place where it had demonstrations nearby, it should know roughly what to do, kind of just by doing things that are similar to what the demonstrations showed in the places that are around this point. So now, we execute the motion of the robot using its brain, and we would get a trajectory like this. So I think in paper, this looks pretty reasonable. But in reality, things are a bit more complex. So let's imagine that we have these two tomato settings, and we are going to see some people harvesting these tomatoes. And we could imagine that we could, for example, track the hand of the person harvesting the tomato and use this as data to train our robots. So on the left, we have this case where this person is using both of its hands to harvest the tomato. And it's a big tomato, so for example, it can only pick one at a time. And then on the left, we can already see that the tomatoes are smaller. There's actually a bit of an occlusion with a leaf of the plant. So the technique might be a bit different. First, the person actually moves a bit the leaf with the hand, then picks one tomato, and then keeps one tomato inside the hand, and then tries to pick the next one. So we have just here two situations only that we can see with tomatoes that kind of illustrate that in practice, actually getting enough data in all of the possible situations that the robot could encounter can be quite challenging. So we can see that some issues arise. First, to actually learn nicely using imitation learning, we might need too many demonstrations. And the other thing is that also in the real-world setups, we require reliable and safe behaviors. And again, we cannot really have this if we cannot cover properly the space with demonstrations. So to address this, in my research, I focused on two problems of imitation learning. On one side, we have data efficiency. We want to be able to learn and generalize easily from fewest data as possible. And also reliability. We don't want robots, in this case, doing a mess, for example, in the kitchen of our house. And to address these two topics, I used two different families of methods that belong to different types of approaches. So on the top, I have interactive imitation learning, and in the bottom, inductive bias. Interactive imitation learning helps with data efficiency, and inductive bias actually can help both with data efficiency and reliability. So let's start with interactive imitation learning. So we go back to our imitation learning setting that I showed before. But this is also a bit of ideal. This is not exactly what would happen if we have some demonstrations. Actually, if we have a demonstration, and again, we give this data to our brain to train it, maybe it's going to roughly follow this demonstration, but it's not going to be perfect. So maybe at the beginning, we see that it's actually following the blue line, but eventually it diverges away. So it wouldn't really work. So we could say, okay, no problem, we can just collect more data. We put the robot in a different initial condition. We again control it and collect another trajectory. And this could be fine, but the same question could apply to any case. If the robot now moves to a different initial condition, since actually what it's learning might diverge from the data that we gave to the robot, we can't really know what it's going to do. So our best possible solution is just to put the robot in many situations as possible, collect as many as data as possible in a very naive way, and just give everything to its brain to train it. And now, the robot is going to be more intelligent. The problem with that is that, it might be very data efficient because we're collecting more data than what is needed. So interactive imitation learning addresses this topic by directly learning over the trajectories that the robot itself would generate. So in this case, now we have this example of a car, which is better, I think, for illustrate this case. So we have this red trajectory, which is the car driving around the road. And we can see that in some cases, the car is actually not doing what it's supposed to do. It's not driving properly. So a human can intervene, for example, in different situations and tell the robot how it should change its own behavior. So in different points in time, it should tell, actually, in this case, you should move more to the left, more to the right, and more to the left again. We can use this relative information to improve the behavior a bit. So now the robot is a bit smarter, but still maybe it's not perfect. But again, there's no problem. The person, again, can appear, give some feedback, and improve the behavior again. Eventually, hopefully, if we do this enough, we're going to learn a nice behavior. The good thing about this is that we only collect data where the robot needs it, because now we actually know what the robot is going to do because we're directly observing it, and this makes the problem much more data efficient. So an important part of my thesis actually was exploring these methods and how we can use them in the best way possible. This is just an example of how this works in practice. So in this case, we have this robot, and you can see the lights are turning on when I was clicking some buttons. Basically, here I'm correcting the robot to move more to the front or to the sides, and we want to teach it to dribble this ball to the goal. So the robot is trying to dribble the ball. Sometimes it's doing things that wouldn't really work, but it's fine. I'm just correcting the robot and doing this multiple times. So yes, this is the result after some time of training. And then for the second part, we also have inductive bias. So let's go back again to our example of imitation learning. We have here our demonstration, how to reach the star. The robot, let's say that it learned properly this time, so it knows what to do. And now, let's say that we put the robot again in different initial conditions, but we don't give demonstrations here yet of what the robot should do. So the robot is basically just going to make a guess. It's in a place where we didn't show it what it should do. So it has a model that is just going to guess what to do. And as a consequence, you have these trajectories that don't really work. But a good question to make here is like, why did the robot make these specific guesses for trajectories and not others? What happened here? And there's the concept of a bias that actually it's very important in this happening. Basically, the robot or its brain has some bias that is forcing him to choose some solutions over others. So maybe we can use this to our advantage. So let's imagine that now we have a different computer algorithm for the robot with a different type of bias. Then for the same initial conditions, if we don't have data, we could get different trajectories. Now they're doing something different. Again, we could have a different bias into our system, and we would get these yellow trajectories. So basically, depending on which bias we're giving to the system, which solution is choosing in places where we don't have data. So this is the case where we are not putting any bias like on purpose into our system, no inductive bias. So it's not really working. But in the case of this example, which is actually a reaching task, where before collecting any data, we know in this specific case that the robot should always reach the star. This is some prior knowledge that we have about the problem. So even if we don't have data in different parts of the space, the robot should always reach the target. So maybe we could find a way of creating some inductive bias that we could put into our system such that even in places where we don't have data, the robot will always converge to the goal. So in these ways, in some regions of the space, we can still learn from data, but in others, if we don't have data, at least we have some default behavior that is more reasonable than other solutions. This is an example of actually a reaching task that I learned in one of my work. In this case, we want the robot to hang this hammer. As you can see, actually, the robot should always reach the hanger. So these actually are prior knowledge about the problem. But also, of course, I gave some demonstrations to show the robot exactly how the hammer should be placed. So, yep, that's my presentation. I hope now things are a bit more clear about my dissertation. Thank you.